Hey class, so here's the next question for you all. As you can see, we have these three blocks in a very kind of precarious situation. We got this 12 kilogram block on top of a 9 kilogram block, but the 12 kilogram block is fixed to the wall, so we know it's going to remain stationary because as the mass m drops, it will pull on the 9 kilogram block but leave the 12 kilogram block stationary. So as we look at this, we're given coefficients of kinetic and static friction between the two blocks and between the 9 kilogram block on the ground, and we're asked the acceleration of the mass m, which has a mass of 15 kilograms. So the first question we have to ask is, will this system move at all? Because if we don't overcome the static force of friction, then it will not accelerate at all. But before we even jump into that, we should always start with good free body diagrams. So here we really have two options. We can do free body diagrams for your objects individually. So for our 9 kilogram block, we would have the normal force from the 9 kilogram block pushing up. So maybe I'll call that Fn1 maybe. And that's from the ground up on the 9 kilogram block. Similarly, we're going to have the weight of the 9 kilogram block, so M9G pushing down, and then we'd also have kind of the equal and opposite, what I'd call maybe Fn2, pushing down on the 9 kilogram block, and that's really just going to be the weight of the 12 kilogram block pushing down, because the 12 kilogram block is going to have that Fn2 pushing upward on it. And then there's actually going to be two forces of friction. There's going to be the force of friction 1 at the ground, and the force of friction 2 at the kind of interface between the 9 kilogram and the 12 kilogram block, and then there's going to be a tension pulling to the right. The hanging mass is much simpler. It just has the tension pulling up and its weight, capital Mg, pushing down. So the first thing we have to see as we look at some of the forces in the x direction equals max for the 9 kilogram block, we see that we have T minus force of friction 1 minus force of friction 2 equals max. So we need to check and see, first of all, if both of these are at their max static force of friction, will they be larger than the T force pulling? If so, this system will remain stationary. So we need to calculate the max static force of frictions first. So let's go ahead and do that. So the force of friction 1 static max, which is kind of a mouthful, right, is going to be equal to mu S1 multiplied by Fn1. And normal force 1, if we do sum of the forces in the y direction for the 9 kilogram block, so keep in mind all of what we're seeing here is for the 9 kilogram block. If we do sum of the forces in the y direction equals may, we would have Fn1 minus mg minus Fn2 equals 0. So what that would give us is a scenario where Fn1 would end up being equal to basically the 9 kilogram mass plus the 12 kilogram mass times gravity. So we'd have a normal force that's basically equal to 21 kilograms times gravity. So if we go ahead and calculate this, our force of friction max 1 should come out to be equal to our coefficient 0.25 multiplied by 21 kilograms multiplied by our 9.8 meters per second squared. And so what we would find is that force of friction static max for the bottom of the box comes out to be equal to a grand total of 51.45 newtons. Now similarly, we'd have to do the same thing for the second box. So the force of friction 2 static max is going to be equal to mu S2 times Fn2. Now Fn2 again is the normal force at this interface between the two blocks, and Fn2, you can find this by doing some of the forces on the 12 kilogram block, but it's just going to be equal to the weight of that 12 kilogram block. So the force of friction 2 static max should come out to be equal to 0.45 multiplied by 12 kilograms multiplied by 9.8 meters per second squared. And so the second max static force of friction should come out to be equal to, this one comes out at 52.92 newtons. So if we add those together, the total net static force of friction comes out to be, the sum of those two comes out to be equal to, let's write this out, 104.37 newtons. Now, if we look at the smaller box, just block M, and we do sum of the forces on it equals MA, we would have the tension minus the weight. And so if it were pulling at its hardest and not accelerating at all, our tension would just be equal to that weight. And so at the maximum, at max, the tension would just be equal to 15 kilograms multiplied by 9.8 meters per second squared, or 147 newtons. So all of that was to prove that what we have down here, max static, is less than the pull of the block M, therefore the system will not accelerate. All right, well, that was fun. So what that means then is we have to look at a situation where things are actually going to be accelerating. So we can erase much of this work here and pick up where we left off up here. So as I mentioned earlier, we could at any point, if we chose to, look at the system as a whole, in which case, again, the tension would be internal, and you'd have big mg pulling down here. You'd have the two forces of friction, so FF2 and FF1, which we now know are both just kinetic. Oops, FN1 pulling up, FN2 pushing down, and the 9 kilogram mass. So that would be your two free body diagrams. Again, you do have tension, but it's an internal force, so it would cancel out. But either way, again, if you do the system as a whole, or if you deal with them individually, you'll get the same answer. So I'm going to go back to dealing with them individually here, and I'm going to rewrite what I'm doing here with the 9 kilogram, or the big M, sorry, just to make it a little more clear. So here's the work for the 9 kilogram mass. Over here we're going to do big M, so we're going to do sum of the forces in the Y equals MAY. And now I know that AY for this guy is going to be down because the acceleration for the 9 kilogram block must be to the right. So I'd have T minus big MG equals big M times negative A. So T would be equal to big M G minus big M A, which I could then plug in to this equation up here. And what I would get when I combine those two is, I'm going to write it down here at the bottom to make sure I have room, big M G minus big M A minus force of friction 1 minus force of friction 2 equals the 9 kilogram mass times A as well. So from there you should be able to do some algebra to solve for A. What you would get when you do that algebra is A is just going to be equal to big mg minus your two forces of friction, all divided by the sum of your masses, big M plus the 9 kilogram mass. So what this comes out to be equal to again is big M, so 15 kilograms, times 9.8 meters per second squared minus mu k1, which we have a value for, times the normal force at the bottom surface, so that's 21 kilograms times 9.8 meters per second squared, minus mu k2, which again we're given, multiplied by the normal force between the boxes, which is the 12 kilogram mass multiplied by 9.8 meters per second squared. And you get all of that divided by the 15 kilogram mass plus the 9 kilograms. And that altogether should give you your net acceleration of the system, which again, if all the numbers come out correctly, should be 3.37 meters per second squared. Box worthy for sure. That's worth like 2 boxes. That was a long one. So, hope that helps. Keep up the good work.